मैं राजवीर सिंह शेoran एसोसिएट प्रोफेसर इन केमिस्ट्री SRR मरका गवर्नमेंट PG कॉलेज झुंझुनू. First of all, good afternoon to all the MSc final year students. Today we will start a new topic of your paper second, kinds of reactions catalyzed by enzyme. So in this topic we will discuss nucleophilic displacement on a phosphorus atom. As we know, phosphate esters play a central and unique role in biochemistry. The genetic information of all living organisms is stored in phosphatidyl polymer, DNA and RNA. The genetic information is translated into proteins via ribose nucleic acid, means RNA. The di and triphosphates of nucleosides are important energy carriers, as are other phosphorylated compounds. Groups are often activated by phosphorylation. Energy transaction work and movement is generally mediated via the hydrolysis of nucleoside. So we will discuss in this in this topic, nucleophilic displacement on phosphorus atom is as discussed below. Unlike carbon, which forms only stable tetravalent compounds, phosphorus forms stable trivalent, tetravalent and pentavalent compounds. A phosphoryl transfer reaction is such as given in this reaction: phosphate plus alcohol, then phosphate ion PO3 2 minus and alcohols. Then can proceed by either two general types of mechanism analogous to SN1 and SN2 mechanism. Means SN2 mechanism of carbon chemistry. In dissociative mechanism, there is first the elimination of living group to produce unstable metaphosphate intermediate, and then the rapid addition of nucleophile as shown in the following reactions. In an associative mechanism, there is first of nucleophile to give a pentavalent transition state followed by the elimination of living group. This mechanism is subdivided further. There is an in-line mechanism in which the attacking nucleophile enters opposite to the living group, and there is an adjustment as shown in the following mechanism, in which the nucleophile enters on the same side as of the living group as in the given reaction. The adjustment mechanism involves an addition steps which is consequences of symmetry of intermediates. The pentavalent intermediate is trigonal bipyramidal, in which the groups assume either of the two topologically different positions, and means equatorial position, or it may be apical. In a line mechanism, the entering and the leaving groups naturally take up an apical position. In adjacent mechanism, however, the entering nucleophile is apical, whereas the leaving group is equatorial. For leaving group to be expelled, it must move to apical position. There is required by the principles of microscopic reversibility. Groups enter apically and so must leave apically. The movement occurs by a process termed as pseudo-rotation, as illustrated in the following example. In this, phosphorus is in the central atom or apical position by OR group and equatorial position by OR dash, and it gives in the product OR dash becomes apical and OR group attack at equatorial. Similarly, the stereochemical consequence the phosphoryl group has the same tetrahedral geometry as saturated carbon compounds. A direct inline associate reaction between two substrates leads to inversion, as would an line dissociative mechanism. Although a dissociative reaction in solution would generally lead to racemization, the stereochemistry in an enzyme reaction is governed by the spatial arrangement of substrate. The adjustment associative mechanism leads to retention of configuration, as in SN2 reactions. In an enzyme reaction, there is the fourth possibility that a covalent intermediate is formed with a nucleophilic group of enzymes. Now, multiple displacement reactions and the coupling of ATP cleavage to undergonic process. A. Multiple displacement reactions. One complicating characteristics of alkane halogenation is that the multiple substituent reaction almost always occur. We know the halogenation of methane produce a mixture of monohalomethane, dihalomethane and trihalomethanes and tetra. This happens because all hydrogen atoms attached to carbons are capable of reactions with fluorine, chlorine or bromine. Now let us consider the reaction takes place between chlorine, methane as an example. We can take an example, suppose methane reacts with chlorine, so it forms chloromethane and HCl. As the reaction progresses, however, the concentration of chloromethane is in a mixture increases and second substitution takes place. Chloromethane reacts with again chlorine to produce dichloromethane, and dichloromethane products can then be reacted to form trichloro and trichloromethanes as it accumulates in a mixture can react with chlorine to produce tetrachloromethane. Now we can take another example, for example isomeric monochloro products, for example isobutane reacts with chlorine to form isobutyl chloride, approximately 48% product is formed and tertiary chloride is formed. So in this mechanism we can take reactivity and selectivity. Means if a compound is more reactive, then its selectivity will decrease. So in neopentane, if it reacts with chlorine and heat light, then it contains neopentyl chloride. So suppose we take isobutyl chloride, then 99% product is tertiary bromide and isobutyl bromide is trace. This occurs due to a factor which we know very well, reactivity and selectivity. Since we know chlorine is more reactive than bromine, so reactivity of chlorine towards tertiary carbon will decrease, and when bromine is less reactive, then its selectivity will increase towards the tertiary carbon. It means tertiary product is formed more. Now coupling ATP cleavage to undergonic process. The energy of reaction which is available for the performance of usual work is designated as free energy or delta F. Energetically, reaction may be classified either as exergonic or undergonic. Exergonic reactions have a negative delta F and tends to proceed spontaneously, such as hydrolytic reactions. On the other hand, the undergonic reactions with a positive delta F must be coupled with an exergonic, that means negative delta F reaction. So coupling mechanism, we know all animals and other living organisms depend upon the oxidation of carbohydrates as their main source of energy. There must be chemical method for trapping the energy of this reaction, since organism functions under conditions of constant temperature and pressure. Now a question arises, how energy can be trapped from exergonic process and made to do useful work? The only manner in which the chemical energy is transferred from one reaction to another by a common reactant. Means, for example, A is equivalent with B is equivalent with C. So delta F0 comes out to be minus 4110 calories, and in the second, when B is equilibrium with C, then we can say delta F0 is 1370 calorie plus. So the delta F0 for overall reaction at 25 degrees centigrade is minus 2740 calories, and the overall reaction is exergonic. So A is thereby converted into C, and this reaction A equilibrium with B has been used to drive the endogenic reactions B give rise to C, and this reaction can be proceeded by an absence of reactions A equilibrium with D. This is coupling mechanism. Same coupling mechanism may be introduced to ATP cleavage to undergonic process. The scientist Lohmann 1929 demonstrated stepwise degradation of ATP, adenosine triphosphate, to adenosine phosphate and adenylate acid. So we can say in the following example, phosphogen, the substance of phosphorins vertebrates the arginine phosphate inverted. The reaction first demonstrated these substitute substances to exist in equilibrium with ATP. For example, creatine plus ATP give rise to ADP. ADP plus creatine phosphate. So delta F0 is also small. This means that the energy of ATP has been smoothly transferred over to creatine phosphate. It also means that the reaction can be tipped back and forth the relative age. Now transfer of sulfate. How post sulfate can be transferred? This is given in the following reaction. Methanol when reacts with H2SO4 then H2O plus methyl hydrogen sulfate distillation it gives rise to dimethoxy sulfate plus sulfuric acid. So transfer of sulfate is a bioorganic process too. It takes place in process of enzyme also. For example, the transferences transfer sulfo group to oxygen and nitrogen atoms of suitable acceptors. So in this example, we can say, now what is enolic intermediates in isomerization reactions? And those reactions in which isomerization takes place, we can take the example of 2-pentanone. Its enol form, it can be converted into keto form 2-pentanone. So enol form of acetamide, we can convert it to keto form of acetamide. So these are compounds which determines the acidity of alpha hydrogen, removal of protons, that is acidic alpha hydrogen generates an enolic alliance intermediate stabilized by delocalization of negative charge to oxygen atom of carbonyl. So this is shown in the following base catalyzed enolation reaction. So in the similar way, we can say a methylene group alpha to a carbonyl group is called active methylene group. This is enolation. That is, isomerization can be catalyzed by a base, alkoxide anions like this. Aldose sugar are tautomerized into 2-ketose enzyme catalyzed reactions. So in glucose 6-phosphate isomerase brings about following aldose ketose interconversion. Suppose for glucose 6-phosphate, it is converted into cis-enonediol. Then again glucose 6-phosphate isomerases. Then fructose 6-phosphate is formed. Now enzyme catalyzed decarboxylation and carboxylation. So decarboxylation and carboxylation enzymes are responsible for both the formation of carbon dioxide from organic substrate and for the incorporation of carbon dioxide in molecules. So no general mechanism can be presented since the cofactor requirement of each enzyme catalyzed system vary with type of substrate attacked, alpha keto divalent atoms and then thymine pyrophosphate like this. So this carboxylation enzymes ribose diphosphate divalent cations are given in the following 5.1 table. You can see pyruvate, it gives rise to acetaldehyde plus CO2, pyruvic carboxyl enzyme. Then oxylactase, it gives rise to pyruvate plus CO2. So oxaloacetate carboxylase, then malate plus TPN plus give rise to alpha keto glutarate. Then maleic enzyme we can take, or like this. You can see carboxylating enzymes, ribose diphos plus CO2, it gives a 2,3-phosphoryl glyceric acids. So thank you.